All right, I'm going to guess I have control. So we're talking about text data now, and those that arise from answering open-ended questions. And we're looking into automated classification of those text data and looking at a tool called BERT. All right, so I am controlling, oh yeah, it's working. So classifying answers to open-ended questions manually is time-intensive and not reproducible. The goal is here to classify open-ended questions into predefined categories automatically. Traditionally, I've been at this for a few years. Traditionally, what we do is we manually code a few hundred texts. And so we have a training data set, then we turn text into n-gram variables. N-gram variables are basically frequencies of how often individual words occur in the text. It's a little bit more to that, but I'll leave it at that. And then we use what I now call traditional statistical learning algorithms to classify the remainder, the unclassified open ends. And when I say traditional statistical learning algorithms, I'm talking about random forest and boosting and support vector machines and things like that. Well, I'm trying to figure out, how do I get back here? Well, let me start here. So, yes, okay. So for there's a new language model, BERT, that is better at prediction and classification, and switching from the traditional paradigm, the statistical learning, to BERT may therefore improve classification. And this is very promising, especially on hindsight. Not as much 3 years ago, but it's not obvious that BERT will work here well because it's largely, or at the time was largely, unproven for social science surveys, and it's used in a completely different context by the computer scientist in much larger training data sets and on completely different kinds of data, like Reuters newsgroup data, which is very different from the kind of survey applications I have in mind. And so the goal is here, should we use BERT for automatic classifications instead of the traditional methods? Now, in general, when we try to improve prediction or classification, then the easiest way to do that is to just get more training data, because then we typically gonna predict better. That's especially true for the answers for open-ended questions, because there we typically only have like 500 open ends that are pre-classified, or maybe even less than that. Now, the idea that the computer scientists came up with here is to borrow strengths from other much larger text data sources like Wikipedia. And I don't mean a little bit of Wikipedia, I mean all of Wikipedia, everything that's in the English language, everything. But of course, Wikipedia has absolutely nothing to do with classifying a particular question for my open-ended text answer. And so how can we learn something from the classification for open-ended questions from data that really have absolutely nothing to do with it? So the answer that the computer scientists came up with is to use this to train a language model. So what does a language model mean? When I heard that, I thought, okay, great. That means that's a model that understands grammar and all the rules and how it works and what comes before what. And language models have absolutely no idea about grammar. They know nothing about grammar. All they are is they're good at predicting. They're good at predicting words that are missing in the middle of a sentence that follow. They're good at predicting tokens that may include punctuation or emojis or anything. So missing words in the middle of the sentence, a period at the end of the sentence. So when you predict the period, then you know the sentence is over. And then they can also predict the first word of the new sentence. Now, we have two data sources now. We have the data we're actually interested in, my answers to the open-ended question, and we have Wikipedia or some other vast array of data. And so we have also two steps. First, we pre-train a language model that understands, meaning it's good at prediction language. And then second, we use that pre-trained language model that really can predict words and fine-tune it and tweak it fine tuning. So we have to do two things. We have to pre-train the language model so that it can predict well, and the fine tuning, which does the specific task at hand. Okay, we only do the second task as end users. The first, the language models exist in the web. So there's this tool called BERT, which means bidirectional encoder of representations from transformer. Complicated words. Given that we lost a few minutes, I will ignore what I was going to say. The most important thing for BERT for training is that first task there is mask prediction. And on the next slide, I have an example. Yes. So BERT simply hides 15% of the words that it has at random. Right. So, and here I have an example. Original sentence, well, you see the sentence, and some words are bolded, and those are random words. They're supposed to be 15%, here it's a little more. And you see the masks that it replaces down there. And BERT basically builds the language model by predicting those words as good as it can. This can take a long time. It's gotten faster, but really too long for the average human. You cannot do that on a laptop, not in human time. So I'm trying to advance again. Okay, there we are. So we can think of the BERT thing as the yellow box. And we have the sentence going into the box from below, and the sentence might be CIPHER is a great conference. So we have the CLS token, which means there's the beginning of a new new sentence or new segment. CLS stands for class, and then I have the word, and this continues. These things are encoded into 768 dimensional vectors, and then the magic happens inside. You can think of it as a very complicated neural network. It's a variation on a neural network related to transformers. And then as output, you get the true words as output. BERT iterates through and it optimizes the millions of parameters that are inside it, millions of parameters, such that it predicts the output words as good as it can. Now, 85% of the words it can see, but the other 15% it cannot. Once it has done that to a satisfactory degree, it's pre-trained. And at that point, I don't need the output words anymore. And instead, I just use that initial token, beginning of the sentence, because that captures basically the meaning of the sentence. And I'm adding one linear layer in here. Linear layer is a term from a neural network. It's basically one more group of arrows in there. And then straight I go into the predicted class, which is either, well, it's one of several categories or it's a multi-label task, right? So most of the action happens down here, and then I just add one layer, and during fine tuning, I basically need to predict the weights that are here in the end there. Now, there are two steps, as I've said, pre-training and fine tuning. And I'm waiting to advance. Okay, there we are. Two sets of parameters. There are the millions of parameters in the BERT layers, and then there are some extra variables, parameters in the linear and output layers. So you can either keep the parameters in the yellow box in BERT frozen and just estimate the remainder, or you can also let the parameters in the yellow box change a little, but only a little, because if you change it a lot, then what's the point of pre-learning them? So you can allow to change them a little, and still you have to estimate, of course, the extra parameters above from the last layer. And it's not completely clear which way, whether it makes sense to change the frozen parameters or not. Okay, I'm trying to advance. Okay, nope. Yeah, so frozen parameters refers to only using, not changing the parameters in the yellow layers, and fine tuning refers to you are allowed to change them a little. The other parameters have to be added anyways. I'm trying to advance again. Okay, advance again. I'm going through this a little faster because we've lost some time, right? So now I use 2 data sets to try this out, and I'll show you exactly what I'm trying out. And for the purpose of the presentation, what is important only is there's a question, there are answers. In this case, we have actually small data set, 580 samples or observations, and it's classified into 4 classes, 1 of 4 classes. Okay, I'm advancing. The next data set has 1,200 observations and classified into 11 classes. So 4 classes versus 11 classes. And advancing. Okay, and so what I'm comparing now is I'm using the 3 traditional methods, SVM, random forest, and boosting. That's XGB is a variation on that. And then I'm comparing that with BERT and with frozen BERT. So I'm looking at these 5 methods and look like which gives me the best prediction. Advancing. Okay, yeah. So if you look at the horizontal axis, this is the amount of training data I'm allowing. And they're different amounts. I start with just 100 observations, which is really nothing. And I go up to 400 observations as training data, and then I predict the rest. So on the vertical axis, you see classification accuracy. So higher is better. And you see what sticks out. The line at the bottom with the triangles, that's really, really a lot worse than everything else. And the method that corresponds to the line at the bottom is frozen BERT. So based on this data set, you never want to freeze the parameters. And it's a little bit surprising because you spent, so much time and effort to estimate those parameters from all of Wikipedia. And then based on my 100 observations here, then I'm still supposed to change it. So it's a little surprising. We also see that the best method up there, the line with the circles, is BERT. So BERT appears with fine-tuning at the top and the other one at the bottom. And then in the middle, you see all the 3 other methods. They are sort of the same here for classification. Mind you, they are also based on the same n-gram representation of text, right? They're all taking the same input variables. Okay, so advancing the slide. Okay, here's the second data set with really remarkably similar results. Frozen BERT at the bottom does horribly, avoid it at all costs. BERT at the top does best. Maybe there's a bit of an effect that for 100 it does a little bit better, but for 200, 300, 400, sort of there's an incremental effect that it does incrementally better. The other 3 methods are the same. Advancing slide. Okay, so even with tiny data, BERT classifies better than traditional learning methods. Some evidence the advantage is greater for 400 training data than 100. Avoid training BERT at all costs. Now, I want to spend 2 seconds on limitations. This was all done in English, right? So that doesn't matter to the traditional methods, but it matters to BERT because BERT needs a pre-trained language model. When I first wrote the grant 3-4 years ago, that was a big deal because BERT only existed in English. Now we have all kinds of languages. If it's a Western language, you're covered, and many of the other languages also. So it's not really a limitation anymore. The other thing is, from a practical point of view for survey methodologists for using it in practice, this requires Python. And that's a higher skill level. You can't get it with data really. There's a crosswalk from R. I haven't tried it, but really it all boils down to Python. So makes it a little harder. All right, then I think my next slide, advancing, is the last slide. Thank you very much. And I'm sorry about the little kerfuffle there.